In this video, we're going to discuss systems of equations. So I'm going to start off with this first question. Is the point 2, 8 a solution to this system? And so we're not solving anything yet. We are going to get there. We're going to figure out how do I actually take a system and get to its solutions. But right now, we're going to start off the same way we did with just basic equations. Can we determine if something solves an equation? Or in this case, can we determine if this point solves these two equations? So I'm going to take my x and plug it in for my x. I'm going to take my y, plug it in for my y. Same way we've done forever, right? So I had a y. 8 is equal to 5 times 2 minus 2. And let's see if this is a true statement. 5 times 2 is 10, minus 2 is 8. And so that is in fact true. The first equation works out with that point. But the difference between these and just a basic equation, or just one equation, is that we do have more than one equation. That's where the systems get in. Systems just meaning we have multiple equations and it has to work for all of those equations. All those equations have to be true. So I'm going to take my second equation, 2 times my x, which was 2, plus 3 times my y, which is 8, equals 11. Let's see if this is true. 2 times 2 is 4, 3 times 8 is 24, and is that equal to 11? No, that's 28, and that is most definitely not equal to 11. So this is a false statement. So to answer the question, is this point a solution? No, 2, 8 is not a solution to that system of equations. So let's look at another point, same system, but this time I'm going to ask the question, what about the point 1, 3? So why am I choosing these points? Well, I'm just asking the question, right? I'm just choosing seemingly random points, not exactly random. I've chosen them for given reasons, but just asking the question, does this point work in the equation? So we're going to do the same thing that we did just a second ago. I'm going to start by plugging my 1 into the x of the first equation, the 3 into the y. So let's see what happens on this one. We'll have 3 equals 5 times 1 minus 2. And we get 3 is equal to 5 minus 2. 3 is equal to 3. That is true. So just like with the first one, the first equation did work out, but we know that it has to work in the second equation as well. So this time I'm going to take my 2 and multiply it by 1. I'm going to add 3 times 3. We're going to see if that's equal to 11. So we have 2 plus 9. And this time we end up with a true statement. This is true. And so what can we say about this point 1, 3? We can say 1, 3 is a solution. I can abbreviate solution SOLN to the system. You may also see this written, the point 1, 3 satisfies the system of equations. Either thing is true. So we tested our first point in the 2, 8. We said, hey, no, that doesn't work because it doesn't work in both equations. We tested another point. It worked in both equations. So before we get into solving these, let me talk about how many points we should expect to work. Is this the only point that is going to work, or are there going to be others? Well, we just saw that there are multiple x values or multiple xy combinations that work within one equation. And that should be obvious to us, right? Because if we think about this equation, y is equal to 5x minus 2, that is just a line. Y equals 5x minus 2 means we have a y-intercept of 2 and a slope of 5, 1, 2, 3, 4, 5. And so of course I did not hit that mark at all close. Let me try that one more time. So if I have my 2 points and draw my line through them, I can see that there are infinitely many points on that line. So of course there have to be infinitely many things that solve that first equation. But then we're bringing the second equation into it. And notice this isn't in the form of a line, but we could put it there pretty easily. I shouldn't say that it is absolutely in the form of a line, but it's not in the form of a line that we know how to graph right away. But we can put it into that form pretty quickly. I'll move my 2x over, 11 minus 2x. I'm going to divide by 3, and so y is equal to 11 thirds minus 2 thirds x. And so this is a form that we know how to graph. We can see that we have a y-intercept of 3 and 2 thirds, 1, 2, 3, a little bit more. And then we have a slope of negative 2 thirds. I'm going down 1, 2, to the right 1, 2, 3. So just kind of doing a quick ballpark, we would have another line. And what's true of that line? That line, this decreasing slope here, has its own infinite solution set. there are infinitely many things that would solve this line, just as there's infinitely many things that would solve that first line that we drew. However, notice with this system, what I'm saying is I have to solve both things at once. So how many points do we see where they agree? How many points could we choose that they both end up with a valid solution? So for instance, if I chose 2, this second line here would predict this value of approximately, I don't know, 1 or 2, whatever it is. The second line would predict something well above, 7. They have a disagreement. So for that 1x, they have 2 different y's. They both can be solved independently, but when we put them together, there's not one point that can solve that. So where do we see that they can both be solved at the same time? That is only this point right here, their point of intersection, and that is what we've just found. The point 1, 1, 2, 3. And so notice, even with my terrible graphing job here, we can still see that's exactly where they are crossing. So to answer a question, how many solutions should we expect to have? It seems like maybe the answer to that question is 1. And I will stress that for this video, I am only going to work with linear equations, right? Because obviously, if I start working with nonlinear, that changes the parameters entirely, right? If I took maybe a quadratic and crossed it with a line, well, how many possible solutions are there now? 2. If we took some really strange polynomial that's going all over the place, and then put a line through it, how many solutions do I expect then? Any number, right? But for today, if we're just dealing with 2 lines, how many points of intersection do we expect to have? Well, no matter where I place those lines, we would typically expect to have 1 solution. But hopefully you guys are yelling at your screen saying, no, that's not all the possibilities, because what if those lines were in fact parallel? How many times do they cross now? They don't cross. They don't cross at all. They are staying an equal distance away from each other, never going to have the same solutions, right? These 2 lines here, these parallel lines, would never agree on a solution. So here we would have 0 solutions. And then I want to fit these all into one screen, so let me put one more on the screen. There is a third possibility for lines, which is that they actually fall one on top of the other, one sitting on top of the other. And so even though the equations might not look the same at the start, if we were to graph those 2 equations, 2 different looking equations, and graph them, we actually end up with the same line. What that tells us is, just like we did with the one initial line, we have infinitely many solutions. So these are kind of the 3 outcomes we should expect. 1 solution if they cross at just a single position, 0 solutions in the case that they never cross, and then infinitely many solutions if they in fact touch it more than one position or at all positions. Again, this is just true of lines. The second we start taking things that are not lines, we're not dealing with these definitions anymore. We are just looking at lines. So once we have parabolas and circles and all these other shapes, well, then it's possible to have 2, 3, however many solutions. So what I'm going to do next is name these different possible outcomes. The 2 cases over here on the right, these are what we call, these are possible, right? We are ending up with solutions, so we call these consistent equations. Consistent equations. The first 1 solution or infinitely many solutions. If we end up with no solutions, these are called inconsistent equations. Inconsistent equations. Inconsistent equations, just the one sub-example, we have the 0 solutions. Consistent equations, we have the possibility that we have 1 solution, or we have the possibility of infinitely many solutions. So then if we look at these consistent equations, we will always get a solution set for these. So the same way up here, we knew that the solution was 1, 3. My screen's being really slow. There it is. We knew that the solution was 1, 3. We will get a solution set. We will have an x, y that will solve it in both of these cases. Now you might be saying to yourself, how is that going to happen on the infinitely many cases? We're going to get there, right? But we will have a solution set on the left-hand side. On the right-hand side, we're just going to say, no, there's no solutions. Between these two cases, the first case, when we have one solution, we call those independent solutions. And in the case of infinitely many solutions, we call that a dependent solution or dependent solution set. And we will talk about these more as we go through the video. But what we're going to see in the case of the dependency is that one of the variables is actually going to depend on the other. So again, I'm getting ahead of myself here, but just to throw out some terminology, consistent equations, we have at least one solution. Inconsistent, we have 0 solutions. Independent, we have exactly one solution in the case of lines, and that could go up in the case of parabolas, circles. Again, I'm really stressing that. Dependent means we have to have infinitely many. That is the only possibility there. So let's take this system of equations that we saw just a second ago. And this time what I want to do is I want to come up with the solution set. I don't want to have to rely on tracking on being given a solution. I want to find those on my own. So here is that system of equations that we just found that 1, 3 is a solution to. But this time I'm not starting with the question, is this a solution? I'm saying I'm going to find that on my own. So we know what it is. We know that's one and only, but let's see if we can get it on our own. There are two major ways to solve these systems of equations if we're not going to use technology, if we're not going to use some sort of calculator. I should say there's a third. We can always solve these things graphically. I would never solve things graphically because if we end up with something like fractions or irrational values, a graph is going to be really, really hard to read those. So I say that there are two solid ways or two really good ways to solve a system of equations. That is substitution, and the other is elimination. I'm going to look at substitution first because I generally see that students prefer substitution. It's a little bit easier, it's a little bit more, you kind of already done it in the past, honestly. Elimination is going to be a little bit different, so I don't think that one's hard. I think in a lot of ways actually it becomes a little faster, but substitution is a little more intuitive. Substitution, we're going to do exactly what it says to do and substitute one variable in for another. I need both of these equations to be true at the same time. So that means if this is a true statement, I can come down here and replace all of my y's with what I said y was in that very first step. I'm going to substitute in the y into my second equation. So we'll have 2x plus 3 times 5x minus 2 equals 11. And now I'm just going to solve this like I would solve any other equation, any other time I have a variable. I'm going to start by distributing that 3. Then I'm going to combine my like terms. I'm going to add that 6 over to the other side. And then finally I'm going to divide off my 17 and I get x to be equal to 1. And we're halfway there because remember, when we were solving these systems, we're not just looking for a single variable, we are looking for the point of intersection. We're looking for the point that validates both equations. So now that I have my x, I have to go back and get my y. So then I run into the question of which equation do I need to plug into? Well, again, the answer to this is either, because we need both things to be valid. Both equations have to be valid, and so either thing needs to be true. I'm going to plug it into the first one. Why would I plug it into the first one? It's a lot easier. The y is already solved for. So even though you can do either, a lot of times there's an easier one to choose. So I'm going to plug the 1 in for my x. When I do that, 5 minus 2, I get 3. And notice we get the same exact solution that we had just a second ago. The point 1, 3 solves this system of equations. That is the point of intersection. And notice how I've written it as a point because I know that the x was equal to 1, the y was equal to 3. Well, I can very efficiently write that all together as just a point, the point 1, 3. Now, there are a couple of things we do need to be careful of. When we are solving these through substitution, the y will not always be by itself, and it doesn't have to be that we get the y by itself. We could have just as easily gotten the x by itself. So I will substitute the thing that is easiest to replace. Because the y was already solved for, that is much easier to replace in the other equation. Had it been the equation x is equal to 5y minus 2, I would have replaced the x. However, sometimes it's going to be that neither thing is particularly easy. So maybe they both look kind of like that second equation where I have a 2x plus 3y equals 11 and 5x minus 2y equals 6. Well, neither the x or the y are solved for. And so there I have to do a little bit more work. I have to isolate one of those variables first. And the key is I have to make sure I plug it into the other equation. So before I get to elimination, I'm going to come back to this problem. I'm going to do it with elimination. But I do want to do one of those problems that's a little bit more work, just to see what we would have to do to solve this problem using substitution. So here I have 2x plus 4y equals 16, 2x plus 3y equals 6. These two equations, neither of them has an x or y solved for, so I'm going to choose one to solve for the x or the y. I do have the option, I can choose either equation, I can choose either variable. What I will look to see a lot of times is, first off, do any of my variables have a coefficient of 1? That would be the easiest thing to solve for. I don't have to worry about dividing. In this case, I don't. The next thing I'm going to look to see, to make it easier for me, not that because it matters, but because it's easier to solve, is one of my coefficients a factor of all the other numbers in that equation? So if I look at this second equation first, 2 is not a factor of 3, 3 is not a factor of 2, so neither of those would be easier than the other. However, if I look at this first equation, 2 is a factor of 4 and 16. 4 is not a factor of 2. So I believe this first equation, it will be easier to solve for the x, because that is the thing that is a factor. So to solve for x, the first thing I'm going to do is I'm going to subtract the 4y. And then I'm going to divide by the 2, and I have to remember to divide every single term by 2. And that's why it's easier, because I get those nice whole numbers. If I'd solved this for x, I would have a 3/2 y at some point. And that's just, it's messier. Nobody prefers to work with a fraction if you can work with just those whole numbers. So that's why I'm choosing the thing that is a factor of the others. Now that I've solved for that x equation, I'm going to plug into my other equation. So I'm going to have 2 times 8 minus 2y plus 3y equals 6. I'm going to distribute that too, so we get 16 minus 4y plus 3y equals 6. Now I'm going to collect my like terms, and so the y's obviously are the same, but that 16 also needs to move over. So when we subtract that 16 over, it becomes a negative 10. And when we solve that, we get y is equal to a positive 10. Notice this time the first thing I've solved for is the y and not the x, because I actually started with an x is equal to equation. Now I need to take that 10 and I need to plug it back in to get the x, because I do need the x and the y by the time I'm done. And here are my two initial equations. Which one looks easier? Actually, neither. I've actually got 4 equations sitting up here at the top of the screen, and all 4 are true. The 2 initial equations are true. This equation is also true. This equation is also true. And because here the x is already solved for, that is the easiest equation to plug into. It's already solved, so I don't have to do a whole lot of math. I just have to simplify this. We'll have 8 minus 20, and when we subtract those, we get x to be negative 12. And so we end up with the solution negative 12, 10. That would solve this system of equations. So substitution, pretty easy. A little bit more work when we have to solve for one of the variables, but we just do that simple solving, and then we plug into the other equation. Let's talk about elimination. Elimination, in my opinion, is sometimes faster. In fact, a lot of times it's faster. In this first example, this one is an example I think is very quick through substitution. I'm going to show you how to use elimination just to show that it gets to the same place, and then we'll see an example where it's actually a little easier to use elimination. With elimination, the key is I'm going to do exactly what it says, which is to eliminate one of the variables by actually adding or subtracting the two sides. So why can we do this? We can always add or subtract something to both sides of an equation. So if I have a 2 over here and 2 over here, I know I can add a 5 and both sides, that would stay equal. It would stay in balance. Think of it almost like a balance beam. If I have 2 equations, let's say I have 2 balance beams that are currently balanced, And over here I have an x and I have a 5, meaning x is equal to 5. And then here I have a 3 and a 3. Well, I can add those 3's the same way I added those 5's over here, even though it's its own equation. These two balance beams, or these two equations, are in balance. If I add those two things together, x plus 3 has to be equal to 5 plus 3 as well. We've kept them in balance. It doesn't matter if there's 3's there, if there's some completely new variable. I can add those two sides, and as long as those two sides were initially equal, then my new equation stays balanced. So we're going to rely on this fact to use elimination. We're going to add two equations and cancel out one of the variables in order to solve for the other variable. To do this, the first thing I want to do is get both of my variables on the same side. So the 2x plus 3y equals 11. Both the x and the y are already on the left-hand side. Perfect. This first equation, however, I need to move the 5x over to the left-hand side. I must subtract it over, so I have my x's and my y's both on the same side of the equation. If I were to add or subtract these equations right now, I would end up with a negative 3x and a 4y, or if I subtract it, I get a 7x and a 2y. Neither of those is canceled. Do what I did a second ago in the substitution, which is to look for factors. Factors are always going to make my life a little bit easier. And so if I look at the factors, I'm not going to look at the factors within the same equation this time. I'm going to look at the factors of the two equations. I want to cancel off the x's. So I'm saying, is 2 a factor of 5? No, it's not. Or is 5 a factor of 2? No, it's not. So I'm going to look at the y's. Is 3 a factor of 1? No. But is 1 a factor of 3? Yes, it is. So what I'm going to do is I'm going to take this second equation and I'm going to multiply it by a 3. So I have my first equation I'm not changing at all. My second equation, I have now 3 times 5 is negative 15x, and then I have 3 times y, which is a 3y, and then on the right hand side 3 times negative 2 is negative 6. So by multiplying by that 3, I now have the coefficients on the y's to be the same. So if I want to get rid of those, all I need to do is subtract these two equations. I do need to remember that I have to subtract every single term. So I have a 2 minus a negative 15. 2 minus a negative turns into a positive, so I have 2 plus 15, which gives me a 17x. Then we have a 3y minus 3y. They cancel. That was our goal. That was how we designed this thing. Then we have the 11 minus the negative 6, and that gives us the 17 as well. To get x by itself, I have to divide by that 17. I get x to be equal to 1. There's my x coordinate that would solve the equation. That's what we saw just a few minutes ago. Now I have to find my y. I have a few different equations I can plug into. I have the two initial equations, or what I got after I multiplied it by 3. I would never choose a thing after you've made the equation bigger. That doesn't really help. It just makes everything a little bit bigger. So I would choose one of the two initials. Now this is kind of the trade-off between substitution and elimination. Substitution, look at how much work we had to do on the front end to get to that first variable, versus this one we've done relatively very little work. The back end is going to take a little bit more work though, because when we use substitution, we had solved for one of the variables at the front end, and so it's very easy to plug into. Here, I haven't solved for either variable, so I have to choose one of these harder equations to plug into. Not real hard, just a little bit harder. And I'm going to choose the thing that looks easier in my opinion. That would be the second line, because there's only a 1y there. So I'm going to plug that x into the 1 into the x. Negative 5 times 1 is a negative 5. Now I'm going to take that 5, add it over to the other side, and I get a 3. And so we have solved this now. It is the point 1, 3, and that's exactly what we saw a second ago. So we do end up with the same solution. It doesn't matter if we use substitution or elimination, we end up at the same answer. So personal preference as to which one you prefer. I do think it is good to practice both. So in the homework, you're going to see problems that say use substitution, you're going to see problems that say use elimination. Use the one that it's recommending just to get some practice with both. When we get to the nonlinear systems in a couple videos from now, there will be times that one is much easier than another. I think in this first problem, the first method, the substitution, was a little bit easier. Let's take that second equation that I'd done just a few minutes ago with substitution. This one we saw that is a little bit more work than the first to use substitution. This time, let me come back here and let me see if I can use elimination, and let's see if it makes it any faster. So here I've copied my problem over again. I'm going to use elimination, which means I want to eliminate one of my variables. And so if I look at this right now, if I were to subtract, those x's very clearly disappear. So let's do it. I'm going to subtract these two equations. 2x minus 2x, gone. 4y minus 3y is equal to y. 16 minus 6 is equal to 10. And notice in all of, 5 seconds I've ended up at my y variable. Think about how much longer it took that last time. Now, I still do need to go back and plug in to get my x variable. Like I said, this is always elimination a little bit longer on the back end than it is on the front end. So I'm going to take my first equation. It really doesn't seem to make a lot of difference to me in this problem. They look equally challenging or easy, however you want to view it. I'm going to multiply that 4, get 40. Then I'm going to subtract by 40 over. And then I'm going to divide by the 2. And I get a negative 12. If we remember what we got just a second ago, we got a negative 12. We've ended up with the same solution set negative 10 at negative 12, 10. That is my solution. So this problem, I think, substitution much, much faster. So there will be other problems on the homework where it doesn't tell you use substitution, use elimination, it just says solve. And for those, choose whichever one you feel is easier. What I look to see a lot of times is, do I have those variables already lined up? If I do, 95% of the time, I'm going to use elimination. However, if I see that I already have one variable solved for, 95% of the time on those, I will use substitution. So it depends on how the equations are given to me. Now, sometimes it's a little bit of a gray area, right? Maybe there's a lot of multiplication, a lot of subtraction, a lot of things that have to be rearranged. And so then it's kind of making that choice. But a lot of times there is a definite easier way to approach the problem. And like I said, that will be true down the road when we get to nonlinear systems too. So really do practice linear and nonlinear. Let's take another example. So let's take the first equation, 3x minus 2y equals 5. And then I'm going to have 3 times x minus 2/3 y equals 4 plus 3x. So obviously on this one, there's a little bit of work that has to be done first. That second equation is not set up for substitution or elimination because there's just a lot going on with it. So I'm going to take that second equation, I'm going to simplify it first. Here's that place where I was talking about substitution versus elimination. Maybe there's not a clear winner because that second equation just needs to have so much done to it. A lot of times on these, I gravitate towards elimination because I just like it better. But you might be thinking, well, let me go ahead and just get all my x's to one side, and I'll leave the y on the on the left hand side rather, because maybe you'll want to use substitution. I'm going to set it up as if I'm doing elimination. So I'm going to distribute my 3 first, because obviously that needs to be the first step. And then I'm going to go ahead and get all my variables on the left hand side. So I'm going to subtract that 3x over. And by chance, when I do that, I'm left with negative 2y equals 4. So the x's happen to cancel out. That's fine. But what that's just done in my mind too is it's changed what I'm going to use. I'm not going to use elimination on this anymore. I think substitution might be easier because there's already one variable that I can solve for. I can solve for the y. It's just negative 2. I'm not even really using substitution. I'm just solving for that variable that I can find right away. So I end up with the equation y is equal to negative 2. And now I'm going to come back up to that first equation, the only one that seems to matter for the x. The second equation, the x is just dropped out. I'm going to plug that 2 in for my y, so I'll have 3x minus 2 times negative 2 equals 5. And that'd be 3x plus 4 equals 5. So 3x is equal to 1, and x would be equal to 1/3. And so we end up with our solution set 1/3, comma, negative 2. We can always check these the way we did the very first problem. I can always take my points and plug them in if I want to make sure I'm right. That's a really good idea on tests. When you have a couple extra minutes at the end of the test and you just want to make sure you're right. 1/3 times 3 is 1, minus 2 times a negative 2 is plus a 4. So we'd have 1 plus 4, that is equal to 5. If we were to plug it into the second equation, we should see that it should give us a true statement as well. Let's move on to another example. Let's take the equation y is equal to 7x minus 2. And then the second equation, 2x plus 4y is equal to 9x plus 3y plus 4. So once again, I've given you one relatively simple equation, one much more complex equation. And so I'm going to work on solving this second equation first. I'm going to simplify that down, and then we can talk about what we want to use. However, already on that first line, I see y is equal to 7x minus 2. I'm thinking I'm going to use substitution, just substitute that in. But let me just clean up this second equation first. So I'm going to get the y terms to one side. Let's say we want to move the y's to the left-hand side. I'm going to get the x's and non-x's to the other side. So this 3y subtracts over, that leaves me a y over here. This 2y, that subtracts over, that leaves me a 7x. The 1, I add the 1 over, and so I get a 5. And so this second equation simplifies down to a relatively simple y equals 7x plus 5. Now, there might already be a kind of a alarm bell going off in your head, but let me just go ahead and do the substitution and let's see what happens. So what I said I was going to do is I'm going to take this 7x minus 2 and I'm going to substitute into my other equation. So we'll have 7x minus 2 equals, we had a 7x plus 5 over here. So now I have all x's, great. I'm going to work to solve this by moving all the x's to one side. I'm going to subtract that 7x over, and notice what happens. The x's are gone. I'm left with the equation negative 2 is equal to 5. Did I do something wrong? No, I didn't. Remember just a second ago you might have seen something fishy going on or may have had those alarm bells going off. We have what looks to be the same equation, y equals 7x, y equals 7x, but with different y-intercepts. The slopes were the same. Remember what we said about slopes being the same or parallel lines, they never touch. There was never going to be a solution for this system. There are no solutions. This is an inconsistent set of equations. There's never going to be a way to solve this. So we may recognize that a little bit earlier on, but it's not always going to be this obvious. Anytime that we're solving our system of equations, we get to a point where the two sides are not equal to each other, and yet there's no more x's or y's. There's no way to make a negative 2 equal to a 5. That is never true. Before, when we had things like the negative 2y is equal to 4, we can make that negative 2 equal to 4 by multiplying it by the negative 2. But here there are no variables to multiply by, so this was just never going to be a true statement. Does that mean anytime the variables drop out that the solution set is going to be no real solutions or an inconsistent solution set? Not necessarily, so let's take another example. 3x plus 5y equals 1. 3 times x minus y is equal to 8y plus 1. Let me make that a negative 8y plus 1. So the second equation, we have a little bit of work to do. The first equation looks to be in a better format for elimination, so I'm going to shoot for elimination. The second equation, I'm going to go ahead and distribute the 3 first. 3x minus 3y is equal to negative 8y plus 1. Next, I'm going to get the x's and y's to the same side, so I'm going to take that 8y and add it over to the other side. 3x plus 5y equals 1. So this was our first equation, but we've just simplified the second equation. That's what we've done here. And again, should be kind of seeing something fishy going on. But let's take these two equations, 1 and 2, and let's see what happens when we do the elimination. These were two different initial equations that we were given. but they ended up looking the same. So that way, when we do our elimination, I'm going to subtract to get rid of my variables. My x's drop out, my y's drop out. I have a 0 on that side. 1 minus 1, that's equal to a 0 as well. I end up with 0 is equal to 0. Is 0 in fact equal to 0? Yes, that is true. When is that true? That is always true. Did not depend on the x and the y because the x's and y's both canceled out at the same time. So what that's telling me is I have an infinite number of solutions. Or remember, we said that is also a dependent solution set. Now I'm not done with this because I actually have to solve it. But I do want to stress the reason that they canceled out, that we ended up with 0 equals 0, is not just because I did elimination. Let's say instead I'd solved this second equation for y. So y would be equal to, I'll do a lot of math really quickly here just in the interest of time, negative 3/5 x plus 1/5. What if I took that and plugged it into the first equation? We'd have 3x plus 5 times negative 3x over 5 plus 1/5. That should be equal to 1. Let's see if that's true. So we distribute the 5. We'd have 3x minus 3x plus 1 equals 1. Notice the x's drop out. 1 is equal to 1. Still a true statement. We didn't end up with 0 equals 0, but that's not a problem. We still have a true statement. When is that true? That's always true. So it doesn't matter if we use substitution like we did here, if we use elimination like we did the first case. If those variables drop out and we're left with a true statement, we have an infinite solution set or dependent solution set. If the variables drop out, it doesn't matter if we use elimination or substitution, if the variables drop out and we have an incorrect or false statement, there are no solutions. But I did say that whenever we are finding a solution set, doesn't matter if there's one or infinitely many, we want to write down that solution x comma y. We did that for all the earlier examples like the 0.13 or the point, I guess, 10, negative 12 or whatever it was. We wrote down that exact solution. Obviously here, if we're saying there's infinitely many solutions, it's going to be real hard to write down 1, 2, 3, 4, whatever they are, right? And we could find this just by plugging in some numbers. For instance, if I plug in 1 for my x, I get 3, subtract that over, negative 2. So we get y equals negative 2/5. 1, negative 2/5 would be a solution. And I could do the same thing with 2. 2, negative 1 would be a solution. We could do this all day long, so I don't want to list all this out, but what I'm going to do is I'm going to write them in terms of one of the variables. So if I had the variable x, what is my variable y? Well, we already solved it. It's this thing right here. My y would be equal to negative 3/5 x plus 1/5. So there is my solution set right there. If I have a value for x, my y is negative 3/5 times that x plus 1/5. Now, really, when we started this system, our goal was to solve for the variables. And if I leave my answer like this, I really haven't solved for the variable because I still have a variable sitting there. So see this done a lot of times where I'm actually going to solve this variable by saying, let's let x equal some value c. Or a lot of times we'll use the value t too. So let me use t because I think that's what our book does. Where t is just any real number. So this is a slightly more abstract idea that x is a variable and t is now a constant. Both are letters. Yeah, I'm letting x be the variable because x was an equation. Is in the equation, it could represent anything. However, I'm assigning x to be the value t. So it is at this point a set value. I just have not told you what it is, but it is set. And so now I can write my solution t comma negative 3/5 t plus 1/5. So that is my solution set. For the value t, I know the y value is negative 3/5 times that value plus 1/5. I just haven't told you what t is yet. So the advantage to this, we have that solution set. So that way if you said, well, what is it if the x is equal to 1? Well, I plug that in and I get my y. If I have x is equal to 5, then I plug that in, I get my y. And so we have that solution set because we do have infinitely many solutions, but we do have a solution.